Hello all, a very good day to all of you. In this session, we will discuss all the questions that have come from analog circuits in 2019 GATE examination for instrumentation branch. Okay, so in 2019 there are 8 questions, right? So 3 are of 1 mark and 5 are of 2 marks. So total 13 marks have been asked from this particular subject. So the weightage looks little more. Okay, so let us solve all the question one by one. So the first question is, in the circuit shown below, right? The input voltage V in is positive, right? The current voltage characteristic of the diode can be assumed to be exponential, nothing but I is equal to I0 into exponential of V by Vt under the forward bias condition, and where Vt is the thermal voltage, right? And I0 is reverse saturation current. Assume an ideal op-amp, right? The output voltage proportional to what, right? So what is the ideal op-amp, guys? Ideal op-amp is op-amp whose gain is infinity, right? Whose input resistance is equal to also infinity, whose output resistance is 0, whose bandwidth is infinity, right? This is my ideal op-amp. Okay? Also, you can see in the circuit, there is a feedback from output to the inverting terminal, nothing called negative terminal. Okay, and we know whenever there is a negative feedback, like you see, there is a feedback from output to negative terminal. Whenever there is a negative feedback in a op-amp, it obeys a principle that is called virtual ground, right? What it says, right? The voltage at the positive terminal is equal to voltage at the negative terminal. So that is called virtual ground. It will obey only when the op-amp operates in negative feedback. So using this principle, we see voltage at positive is equal to 0 volt, right? So voltage at negative will be equal to also 0 volt, right? Now the current is I, right? Since it is an ideal op-amp, there is no current into the negative terminal. All of the current will pass through this 1K resistor, right? So now applying a simple KVL, right? What is V out? V out is equal to 0 minus I into 0 minus I into 1K, right? This implies V out is equal to minus 1K into I, right? Is equal to minus 1K into I. What is I, guys? I is given I0 into 8 power of V by Vt. What is V? V is nothing but the voltage across the diode, nothing but V anode minus V cathode. Here V in minus 0. So V is nothing but V in minus 0 is equal to V in by Vt. Okay. So you could see V out is proportional to exponential of V in by Vt. So the answer should be option C, right? Let us see the next question. So in the circuit shown below, right? Sorry. And the correct biasing condition for typical operation of LED, light emitting diode, photodiode, and generator diode. So you know this we already know, but let me tell you little briefly. Okay, if you take a LED, right? If you take a LED, right? So it is nothing but a diode, PN junction diode, right? So in a PN junction diode, we know at the junction there is a depletion width, right? That we already know. PN, this is nothing but your depletion width, W. Okay. So when I apply a forward bias, right? Means P side is positive, N side is negative, right? What will happen? Current will flow, right? The holes will move from P region to N region, right? And electrons will move from N region to P region. Okay, so what they will do during the movement, there will be some recombination in the depletion region, right? Mostly. So because of this recombination, what will happen? Whenever a electron and hole recombine, light will emit. That is the operation of my LED, right? So because whenever they recombine, what will happen? Electrons from conduction band will be jumping to valence band, right? This electron will be jumping from conduction band to valence band, and it will combine with the hole. Okay, what will happen in that process? The energy difference, right, almost around Eg will be given as a form of light, right? So this is the operation of a LED. So because it want a current to flow, so that the carrier will flow from P to N and N to P. Then when they recombine, light will emit. So the LED should be in forward bias, right? Second, given photodiode, right? Photodiode, right? We know in a photodiode, first you see what photodiodes do. LED, what it does, it converts the electric energy, right? Electric energy to light energy, right? Similarly, what photodiode do, right? It is the opposite. It converts light to electricity, right? So if you see, right, the main aim of photodiode is nothing but detection of light, right? Light brightness, you can say. So it detects the light brightness. So when you expose light to the photodiode, what will happen? There will be some current. Okay, so depending upon intensity and brightness of my light, the current will vary. Then I can detect light. This is the main application of my photodiode. Okay, so let us understand. It should be operated in forward or reverse bias. Okay, so let us take a photodiode. Okay, photodiode. So in a photodiode, yes, there is a P region, there is a N region. In between, there is a depletion width, right? And what I'm telling, a photodiode should be operated in reverse bias. Why? Let me tell you. Suppose this is the depletion width, okay, where at equilibrium W, right? What happens if I apply reverse bias, right? Reverse bias, the P side is negative and N side is positive, right? What will happen? The depletion width will increase, right? We know because it will increase the electric field and depletion width will increase. So it will increase like this, right? W1, W1 correspond to V1, W correspond to V is equal to 0, right? Now we see what is a photodiode. Okay, when you put light, right? When you put light, what it does, it breaks the bond. Okay, everywhere in the PN junction, right? But in the P side and N side, the net charge is 0. There is no field to drive. But in the depletion region, right, there is electric field. You know, this is positive, this is negative. There is electric field like this, right? It's electric field, right? The electric field, whatever, suppose one electron and one hole generated, right? The electric field will push the hole towards left side and will push the electron to the right side, right? So what will happen? And these holes will go, okay, and electrons will go like this, and there will be a current flowing through the circuit I, right? So this I is proportional to the amount of light, right? So depending upon light intensity, the I will vary because the more the intensity, okay, the more the bonds it will break, right? And the more the carriers, and the more the current, right? So thing is, the photodiode should be operated in reverse bias. Because you see, if you apply forward bias, right, the depletion region will be smaller, right? If it is smaller, definitely the carrier generation will be smaller, right? So thing is, if we apply forward bias, the depletion width will be smaller. Okay, if you suppose we apply forward bias, okay, W will decrease, then definitely the carrier generation, right, electron hole pair generation, electron holes pair generation will be decreasing, right? So if we apply forward bias, the depletion width will decrease, the electron hole pair will decrease. Then also, if we apply forward bias, apart from the electron hole generation current, there will be a forward current. Okay, so I will be, because of I generation, okay, plus I forward bias. Then in that case, it is difficult to detect different brightness of light because my total current is mixed with my forward current also, right? So thing is, the aim of detecting light is not fulfilled, right? So it should be operate in reverse bias. What is the advantage of reverse bias? The main advantage is diffraction width is larger. There are, so the electron hole generation will be more, and the current will be directly proportional to the electron hole pair generation. But in forward bias, the diffraction width is smaller, the electron hole generation will be smaller. Also, the current will be mix of generation and forward. So it is difficult to detect the light. Okay, that's why the photodiode should be operated in reverse bias. Okay, let's go to Zener diode. As all of you know, the Zener is always operated in reverse bias, right? Let me just, for the sake of completeness, if you want to plot the Zener IV characteristic, right? Right. So mostly the xenon diode operate as a voltage regulator. So if you go on applying the reverse bias, right? So this is my Zener. Okay. Zener. This is if you apply reverse bias, right? If you go on increasing reverse bias, current will be very small and voltage will go on increasing. After a certain point, right, the Zener will break. When it breaks, the voltage will remain almost constant. It is called breakdown, right? This is called VBR. So when the reverse bias voltage across the Zener is little bit more than VBR, it will break and the voltage across Zener will remain constant. Then it will operate as a voltage regulator, right? So the Zener diode always operate in reverse bias. Okay, so Zener operate in reverse bias, photodiode operate in reverse bias, right? LED operate in forward bias. What is that? So LED is forward, right? This one. Photodiode is in reverse. Zener also is in reverse. So option A should be correct, right? So I just explain very briefly how they are operating. Okay. So let's go to the next question. For the 4 strain gauges in a Wheatstone bridge, configuration are connected to an instrumentation amplifier as shown in the figure, right? From the choices given below, the preferred value for the common mode rejection ratio CMRR of the amplifier in dB would be, right? Guys, first to understand, guys, it is telling the preferred value. Okay, so we need not to compute. Okay, so you have to tell from your logic what it should be, because it is asking the preferred value. What is your preference, right? Not to compute. We need not to compute that value. You have to tell most likely what should be the CMRR, right? CMRR. Okay, so you know CMRR nothing but the ratio between the differential gain by the common mode gain. Okay, and in an amplifier, okay, I want a differential gain to be very high and common mode gain should be very low. So what I want is CMRR should be very high, right? Because the common mode is nothing but noise and differential mode is the useful signal. So I want my useful signal to get amplified and common mode nothing but noise to be get attenuated. Okay, so I want my common mode gain should be very less. So let's go to the first question. First question we see -20. Common mode gain in dB should be always positive, so it's total wrong. Again, second option is 0. I want my common mode rejection ratio to very high, so 0 is definitely not the answer. Then between 3 and 100, okay, what you want is the common mode gain should be very less. So that means I want my CMRR to be very high. So definitely the preferred value, what I prefer is 100, right? So this should be the answer. It's a very easy question, right? For that, you need to understand what is a CMRR. If you know what is a CMRR, I can easily tell you what is my preference for getting CMRR. Okay. Now, let us see this question, 2-mark question. A voltage amplifier is constructed using enhanced mode MOSFET, right? Level M1, M2, M3, M4, shown in the figure. M1, M2, M3 are N-channel MOSFETs, right? And M3 is a P-channel FET, okay? All the MOSFETs are operating in saturation mode, okay? Channel length modulation can be ignored. That means output resistance R0 is equal to 1 by lambda ID, okay, should be ignored, okay, and ignored means lambda is equal to 0, R0 is equal to infinity. This is the meaning of ignorance. So lambda is nothing but channel length modulation coefficient. If it is ignored, it will be 0. That means my output resistance in the drain will be infinity, right? This is the meaning of ignoring channel length modulation, right? The low frequency and small signal input output voltages are Vin and Vout respectively. The DC supply is given VDD, right? All the original MOSFETs have identical transconductance GMN, while the P-channel FET having the transconductance GMP, right? Find the expression for low frequency small signal voltage gain, okay? So guys, before solving this, right, it's a very easy question, should be solved in less than a minute, okay? So before going there, let me tell you, if we have a common source amplifier, right? I'm applying VDD. So this is R. If I'm applying a V in, okay? So there is DC bias there, I'm not ignoring, okay? For the sake of, suppose I want the gain of my common source amplifier, what I have to do? I have to replace all the DC supply with its equivalent AC, that is ground. Then I will apply my input V, and source is grounded. Right? This is source. Okay, we know this is my R. So we know very well what is the gain of common source amplifier. See how we're getting the gain. This input voltage, okay, will change by gate to source voltage at VGS. Then this change in VGS will give me a current of GM into VGS. Here it is V, right? This current will flow through the resistance. The voltage will be 0 minus current into R. So minus GM V in is the current into R. Nothing but minus I into R. Okay. Here minus I is nothing but GM into VGS. GM into VGS is V in into R. So my V out is equal to minus GM V in into R. This implies gain is equal to minus V out by V in is equal to minus GM into R, right? So if there is a resistance from drain to ground, I am applying a input to the gate, then my gain will be minus GM into R, because minus GM V in is the current, that is called small signal current. When it pass through the resistance R, it develops a voltage minus GM V in into R. So this is the common source amplifier. With this understanding, let us solve the question. Okay. So guys, you see, since M1 is a NMOS, right? This is my drain, this is my source, right? And for this is my drain, this is my source. Okay. Since it is a PMOS, this is my source, this is my drain of my PMOS, and for the NMOS, this is my drain, this is my source. Okay. So my first question is, for doing the small signal analysis, okay, first thing is I have to sort all the sources. So VDD should be grounded for the sake of doing small signal analysis. Okay, so VDD should be replaced with ground. Okay, now if I know for this M1, right, M1 gate and drain is connected, right, and both are connected to ground. Okay, so if what I want to know is what is the resistance looking from the source of the M1. Okay, if I know the resistance looking from the source of M1, I can replace it with the equivalent resistance, right? Similarly, if I could know the resistance looking from drain of this M3, then I will replace it with its equivalent resistance. Okay, so if you have solved many questions, you can straightforwardly say when there is no output resistance, right? There is no output resistance R0, right? Then the resistance looking from the source of M1 will be 1 by GMN. Okay, this is resistance looking from the source of the M1. Similarly, the resistance looking from the drain of M3 will be 1 by GMP. This you can know if you have solved many questions, right? So if somebody did not know this, how 1 by GMN have come, so for them, let me tell you how it come. So let's take the case of M1. For the M1, guys, you see, okay, I am looking from the source. I want the resistance looking from the source, and my gate and drain is connected, and both are connected to now ground. Okay, so if I will have to replace by its small signal equivalent circuit. What is the small signal equivalent circuit? I have a gate, I have a source. Between gate to source, I have a current. Okay, like I have shown GM into VGS, right? This is GM into VGS. Okay, this is my drain. So this is the small signal equivalent of transistor M1. Okay, now you see gate and drain are connected. So I will connect gate to drain, and also it is connected to ground. Drain is connected to ground, right? And source. So from source I want to resistance. That means I will apply a voltage Vx, right? And I will measure the current Ix. Vx by Ix will give me the current looking from source of M1. So let me connect one source Vx and let's measure the current Ix, right? This is plus or minus VGS. Okay. First thing we see, yes, What is VGS? If we apply a KVL here, okay, minus VGS minus Vx is equal to 0. This implies VGS is equal to minus Vx, right? Okay. Now you see this node. The current is coming in. We will put a nodal equation at the source. Current is coming in is minus Ix. Current is coming in is minus VGS. GM VGS is equal to 0. Okay. This implies the current Ix is equal to minus GM into VGS. Okay. We know VGS is equal to minus Vx. That means minus GM into minus Vx. So this implies my Ix is equal to plus Gm into Vx. This implies Vx by Ix is my resistance looking from the source is equal to 1 by Gm. Okay. So directly I said that 1 by Gm, but now I have proved for you how it come 1 by Gm. Right. So this transistor can be replaced by a equivalent resistance of 1 by Gmn. Right. This is my first proof. And see, I did not put a resistance R0 here because it is given R0 is equal to infinity, right? Okay. So now we have to see resistance looking from, okay, this is source, this is gate, this is drain of my PMOS. So for PMOS also, okay, what is my circuit? This is connected to ground, this is connected to ground, right? This is my drain, okay. This is connected to ground, right? I am looking from the drain at the drain. The resistance is okay. So same thing I will do. I will connect a voltage source Vx, okay. Then I will measure the current Ix. Vx by Ix will be giving me my resistance looking from the drain of the PMOS. Okay. So let us do the small signal equivalent circuit. Okay. There is a gate. There is a drain. There is a source. Okay. I am having a VGS is the gate voltage and drain to source I have a current source that is nothing but Gm into VGS, okay, and source is grounded, right? Gate is also grounded, right? And I am applying a voltage and it is grounded, right? I am applying a voltage Vx, right? And I have to measure the current Ix, right? Because you see, gate and drain is connected, right? So gate and drain is connected, right? I do not. So gate and drain is connected. So this implies VGS is nothing but Vx because gate is connected, right? And this is not ground. Okay, gate is connected to drain. That means this gate I have connected to drain. That means VG is nothing but Vx. So VGS is equal to Vx. But the current Ix is equal to Gm VGS is equal to Gm into Vx. This implies Vx by Ix is equal to 1 by Gm. Here it is Gmp, right? So we concluded that the resistance looking from the source of M1 is 1 by Gmp. the resistance looking from the drain of M3 is 1 by GMN. So let us do the equivalent circuit. 1 by GMN. Okay, I am applying a V in here. Source is grounded, right? This is driving my another transistor M4, right? And drain to ground, this is ground only, right? Because for small signal analysis, I will make VDD to ground. From drain to ground, I have a resistance 1 by GMP. This is grounded, both are connected. Okay, this is my circuit. So let us, this is V01, this is my V0. What is V01, guys? V01 is equal to, okay, when there is a change in VGS, the current here will be GMVN and the voltage here will be minus GM is nothing but here, GM is nothing but GMN of transistor M1. Okay, this is M4, this is M3. Okay, GMN of transistor M1 into the resistance of drain is 1 by GMN. Okay, into Vn. Okay, so V01 is nothing but GM Vn is the current, GMN and Vn is the current. Okay, flowing through the resistance 1 by GM, so into 1 by GMN. Okay, so let me write it again for you. Okay, the current is GMN into Vn. Okay, flowing through the resistance 1 by GMN, so the voltage will be into 1 by GMN. Okay, so V01 is equal to GMN get cancelled minus Vn, right? Now for the transistor M4, right, it is M4. What is V out? V out is equal to, when there is a change in VGS, right, the current will be GMN into VGS. Here VGS is nothing but V01. Okay, this current is passing through the resistance 1 by GMP, so it will give me a voltage into 1 by GMP. So GMN into V01 is the current, right, into the resistance is 1 by GMP, right? So this is equal to 1 by GMN into, what is V01 is nothing but minus Vn into 1 by GMP. Okay, so is equal to minus get cancelled. It is equal to GMN by GMP into Vin is equal to my V output. Simplest gain is equal to V out by Vin is equal to GMN by GMP, right? So let us see the solution. What is the given? Gain will be option C, GMN by GMP. So it is a very easy question. Okay, first thing is I have to know the gain of a common source amplifier is minus GMN to R. This is the first step. Second step is, if you know the resistance looking from source is 1 by GMN and resistance looking from drain of M3 is 1 by GMP, then in one step only I can get the answer is this one. This is the first step gain, first stage gain. This is the second stage gain. So it will come in one step only if you already know that the resistance looking from source is 1 by GMN, the resistance looking from drain is 1 by GMT. So because we need not to derive in the exam, okay, because we don't have much time in the exam, better we should not derive this in the exam, directly use the resistance and calculate the gain. Okay, let us see the next question. Okay guys, you see in the circuit shown below, right, assume all the comparators are ideal and all the components have 0% delay. Perfect. Okay, means from input to output it will come instantly without any delay. If we apply any input to this circuit, the output will be instantaneous without any delay. In one period of the input signal, V in is equal to 6 sin omega t, the fraction of time for which the output in logic gate will be high, right? So let us first understand. Okay, let the output be here will be x, here will be y, right? If x and y are the output of first stage comparator, okay, what is the output, guys? Out here, the out here is out is equal to, if x is there, here I will get x bar. If y is there, I will get y bar, right? Here I will get x bar into y bar. Here I will get x, this is x, right? Here I will get x into y. Both are ORing here, right? So I will get x bar into y bar plus x into y, right? So this is nothing but a x NOR gate, right? X NOR y. We know the truth table of my x NOR gate: 0 0 0 1 1 0 1 1, right? If you see, if I apply 0 0, I'll get 1 0 0 1. So this is my truth table of the x NOR gate which is there in the circuit, right? So for getting output high, right? For getting output high, what I want, both x and y should be 0 or both x and y should be 1, right? Right? So x, y both should be 0 or both should be 1 to get my output 1. That's clear to all of you? Okay. Now solve the question. Now you see, will, so this is a comparator, this is a comparator, right? For a comparator, okay, if V plus is greater than V minus, now output will be high. If V plus is greater than, like, less than V minus, my output will be 0, right? This is the thing for a comparator. Clear? Now let us do a truth table. X, this is x, this is y, right? Y, okay. Y, right? So what I want, when, so first thing is, let us take condition. First thing is, I have to know when x will be high. Take the condition of 1. Okay. When x will be high, since my V positive is 3 volt, right? So my V positive is 3 volt. What is the condition for my x to be high? And V in should be less than 3 volt, then only my x will be high, right? So V in should be less than 3 volt, right? Then my x will be high, right? For the y, since positive is already 0, so my V in should be less than 0 volt, right? For my y to be getting high, right? So what is the condition for both will be high? Both high. Because if both are high, then only my output will be high, right? So y will be high, V in less than 0. X will be high, V in less than 3 volt. This implies, what is the condition for both will be high? Both will be high when V in less than 0, because less than 0, less than 3. but the common is less than 0. Okay, this implies for my input, whenever my input is less than 0, my output will be high, and at that time my out will be high, right? Only in this condition. Okay, when V in less than 0, my output will be high, because when V in less than 0, both X will be high and Y will be also high, right? So my output will be high. Then we'll take a condition of 0. What is the condition of 0? If my V in is greater than 3 volt, my X will be 0. So V in is greater than 3 volt, then X will be 0. What is Y? For Y, V in should be greater than 0, right? Then thing is, when both X and Y will be 0, V in greater than 3 volt is for X, greater than 0 volt is for Y. This implies both will be high when V in is greater than 3 volt. This is the common point. Right? Greater than 3, greater than 0. What is the common is? Greater than 3 volt. Okay. When both will be 0, then my output will be 1. Okay. So the condition for my output to be 1 is, one condition is V in less than 0. Another condition is V in greater than 1 volt, 3 volt. This is second condition. Okay. So now let's see the fraction of time it is getting on. Take a sine wave, 1 period. Okay. Okay. This is your plus 6 volt. This is minus 6 volt. Okay. So first condition is V in less than 0. This implies this is 0 degree. This is 180 degree. This is 360 degree. Right. This is my. Okay. So the first condition for V in less than 0 and output will become 1 is this one. So during entire period, okay, during this entire period, my output will be 1, because condition for my output to be 1 is V in less than 0. What is the second condition? V in greater than 3 volt. This implies if you take a 3 volt here, right? This is 3 volt, 3 volt, right? Entire duration, my output will be 1. So you know for sine wave, right? This is sine wave. Okay, sine wave 6 sine omega t is equal to 3 volt. This implies theta will be omega t will be either 30 degree and 150 degree. In both the case, it will be 1. So it will be 30 degree here. It will be 150 degree here. 180 minus 30 is 150. Okay. So during this entire duration, my output will be high. So the first condition is V less than 0. The second condition is V in greater than 3 volt. So if you see the fraction of time my output will be high is fraction of time my output is high is equal to, below I have taken total time period is 360 degree, and how much time it is getting on? 150 minus 3, 30, plus this is 180, right? 180 to 360 is 180, 180. Okay, is equal to 120 plus 180 divided by 360 is equal to how much, guys? Let us see how much I am getting. I am getting, let's take the calculator, guys. So 120 plus 180 divided by 360. So I got 5 by 6 is my answer. This option D is the answer. So let me brief you. First condition is my output will be high if both X and Y is 0 or X and Y is 1. Then I got a condition when X and Y will be 1. Why X and Y will be 1 when V in less than 0. At that time, my output will be definitely 1. Second thing what I did is I get a condition when both X and Y will be 0. This is my condition. That also will give me my output 1. Then I have checked during the entire course of one period how much fraction of time my condition is meeting. Okay, that will give me my fraction of time output is 1. Okay, let's see the next question. Okay, so next question is, you see, in the circuit shown below, the light dependent resistance receives a light from LED, right? The LDR has a resistance of 5 kilo ohm and 500 ohm on a dark and illuminated condition, right? Respectively. The LED is off for t time less than 0, right? At time t is equal to 0, the switch S1 is closed for 1 millisecond, then it kept open thereafter, right? Assuming 0 propagation delay in the LED, we have to find out what is true, right? So what it is asking is the condition of light after the switch is opened. So what it is telling? When t less than 0, right? T less than 0, right? Less than 0. LED is off. LED is off. Off means definitely this is. So LED is off means my NP and BJT also is off now, right? Because LED is off means there is no current flowing through the diode. When there is no current flowing through the diode, my NPN also should be off, right? NPN also should be off. So when NPN should be off, means it should be Q also should be 0. Okay, when Q will be 0, guys. Let us take a SR flip flop, okay, and you take Q. Okay, so if S is equal to 1, R is equal to 0, my output will be 1. Okay, if output is 1, if you apply 0, 0, it will go to memory, output will remain 1. Okay, again if S is equal to 0, R is equal to 1, my output will be 0. Okay, if again we will apply 0, 0, then output will remain 0. So 0, 0 is my memory state. So 0, 0 if I apply, whatever state earlier, 1 or 0, the same state will maintain, right? So you see, since my Q is 0, so my S will be either this condition or this condition, right? So irrespective of that, first you see, t less than 0, my LED is off. LED is off means this is 0. This is 0 when it will come, because you see, this is 5K, right? This is 5K. So when LED is off, right? The LDR is 5K, right? 5K. So this is suppose Vx. So let us take a condition t less than 0. Okay, Vx is equal to 5 volt into 1K by 5K plus 1K, right? Because LDR is 5K when light is off. So what is the value? 5 by 6, right? 5 by 6 is equal to 0.8 volt. 0.8 volt means this will be high. Okay, so that means S bar is high. Means S bar high means, so in this 20 greater than less than 0, S bar is equal to high is equal to 1. Simply S is equal to 0. R bar is already tied to high, so R is equal to 0. Okay, so this is the condition of my SR flip flop for t less than 0. For t less than 0, I have my Vx is 0.8 volt, SR is 0 and 0. So 0 and 0 can give me my output 0. If previously my output is 0, so you can assume the output is 0. So light is off. So this is the condition for t less than 0. For t less than 0, I am repeating, the diode is off, transistor is off, the output Q is equal to 0, S and R are 0 and 0. This is all things for t less than 0. Okay, now what I did, I am applying t. Okay, I am applying a so what I am doing now? So let us build a table. Okay, SR time, okay, SR time, then we'll have to see, okay, LED. So this is Q, okay, Q, then LED is off for on. Let us take this one, okay. First, take T less than 0. This is the condition. LED is already given off. For T less than 0, LED is off, it is given. LED is off means Q is equal to 0, definitely. Okay, Q is equal to 0. And let us take a condition Vx also. Right? Vx is, since LED is off, Vx is 0.8 volt calculated. 0.8 volt. So 0.8 volt means it will be high. So this is suppose take X, you take this is Y. The node is Y. Node Y. Node Y is how much, guys? 1, right? Because LED is Vx is this is Vx, right? This is Vx. Vx is 0.8 volt. That means Y is equal to 1. Okay. So T less than 0, LED is off is given. From this condition, Q is equal to 0 and Y is equal to 1. So since Y is equal to 1, Y is equal to S bar. Okay, Y is equal to S bar. So S is equal to 0 and R is already 0 given. Okay. So this is the condition for T less than 0. Then for time 0 to 1 millisecond, my S1 is closed. So time T is equal to 0 to 1 millisecond. Since S1 is closed, right? S1 is closed. So there is a path from here to ground. Diode will be on. Diode will be on means LED will be on. This is my first condition, right? This is my first condition, right? If LED is on, we know when light will be on, the LDR resistance will be how much? Given 500 kilo ohm under eliminator condition. So Vx will be 500 ohm, okay, divided by 1K plus this will be 1K, right? 1K divided by 1K plus 500 ohm into 5 volt. Okay, Joule how much, guys? 1000 divided by 1500 into 5 is equal to 3.3 volt. 3.3 volt. So first condition from 0 to 1 millisecond, LED is on. When LED is on, the resistance will be 500 ohm. So I put 500 ohm here. If you put 500 ohm, Vx will be 3.3 volt, right? Then Vx is 3.3 volt. V negative is more than V positive. So output will be 0. Since Y is equal to S bar, so S will be 1, right? S will be 1. R is already tied to 0. So what it will do? 1 0. 1 0 means Q will be 1. Q is equal to 1. See, for S is equal to 1, R is equal to 0, my output is equal to Q is equal to 1. So I put 1. Okay. So Q is equal to 1 means the transistor will be on. Transistor will be on. Right? Now, T, this is the condition for T is equal to 0 to 1 millisecond. For T greater than equal to 1 millisecond, what happens? This switch is open. Switch is open. So even if switch is open, right? Q is equal to 1. Right? Q is equal to 1. Q is equal to 1. That means LED will be on. Right? Once Q is equal to 1, right? Once Q is equal to 1, right? R is 0. Anyway, R is 0. Right? R is 0. So maybe S is equal to 1 or 0, right? 1 or 0, right? S is equal to 1 or 0, irrespective of S is equal to 1 or 0, my output will be what? See, presently my output is 1. Right? Presently my output is 1. Right? Output is 1. R is always 0, tired. Okay? Irrespective of S is equal to 1 or 0. So presently my output is 1. right? From 0 to 1 millisecond. When output is 1, x is equal to 1, r is 0. So when output is equal to 1, x is equal to 1, output r is equal to 0, right? Now, if r becomes 0 or 1, irrespective of r is 1 and 0, my output will remain 1, right? So x become 1 and 0, no need to see at all. Output will be always 1. When output will be 1, VGT will be on, LED will be on, right? Irrespective of this condition, no need to check at all. Because once my output goes to 1, since my R is already tied to 0, because R I am not changing at all, R is tied to 0. So once my output goes to 1, R is tied to 0, whatever may be the S is equal to 1 or 0, doesn't matter. My output Q will be remaining 1, because once I got output 1, irrespective of S is equal to 1 or 0, my output is 1 only. So thing is, since Q is equal to 1 every time after t greater than 1 millisecond, my NPN will be on. Since my NPN will be on, current will flow and LED will be on. So for t greater than 1 millisecond, my LED will be on forever, because there is no way my Q will be go from 1 to 0. Because once it comes to 1, to go it 1 to 0, I want 1 to 0. If I want my R to be 1. R I cannot make 1, because already I tied to high. Okay, so R I cannot change at all. That implies for t greater than 1 millisecond, my output will be 1 forever, LED will be on forever. Now let us see the condition. Turns on when S1 is closed and remains on after S1 is opened. This is the answer, because here turns on when S1 is closed and turns off, no. Toggles periodically, no. S1 is continuous to remain off, no. So thing is, it will remain on after S1 is opened, because my state of the flip-flop is not able to change. Once it changes to 1, we cannot change to 0, because R1 is already tied to high. That means R is equal to 0. Okay. So I think this is clear to all of you, right? Let's see the next question. In the circuit shown below, all the transistors are N-channel enhancement mode MOSFETs. They are identical and are biased to operate in saturation, right? Ignoring channel length modulation, right? Find the output voltage V out. Okay. You see, since 1 milliampere is flowing here, right? Since 1 milliampere is flowing here, same current will flow here, right? And suppose this is M1 and M2, right? Suppose this is M1 and M2. Since M1 and M2 get are tied, source is common, VGS is constant, right? VGS is same for M1 and M1. VGS of M1 is equal to VGS of M2. Okay, so and current is proportional to VGS minus VTH rho whole square, because there is no channel length modulation. Because if channel length modulation would have been there, it would have been 1 plus lambda VDS. But since it is not there, I have to ignore this effect. Okay, so the current solely depend upon VGS. Since VGS is same 1 milliampere will flow through M2. So I M2 is equal to 1 milliampere, because VGS are same. Okay. Now let's take this is M3, this is M4. Okay. So what is the voltage VGS of M3? VGS of M3 is equal to 6 volt minus 4 into 4K into current is 1 milliampere. This is 1 milliampere. 1 milliampere. Okay. Is nothing but VGS3. 6 minus 4 is equal to 2 volt. Right. Now You see, for this NMOS, right, this is my drain, this is my gate, this is my source, right? For this NMOS, this is my drain, this is my gate, this is my source. And since all are operating in saturation and the same current will flow through the branch, so we know current of M4 is equal to current of M3. This implies half mu n COX double by L of M4. Since all transistors are identical, so double by L I am taking, okay, into VGS minus VT whole square. What is VGS, guys? VGS is 6 volt minus V out. 6 gate is 6, source is V out. VGS is VG minus VS, okay, minus VTH rho whole square. Clear? Is equal to IM3. IM3 again same, half mu n COX double by L into what is VGS? VGS is nothing but VGS3. VGS3 is nothing but 2 volt. So VGS is 2 volt minus VTH rho whole square. What is happening? This thing got cancelled. If you take the square root, 6 minus V out minus VTH is equal to 2 minus VTH. VTH got cancelled. It implies V out is equal to 6 minus 2 is equal to 4 volt. This is the answer. Answer is 4 volt. Okay, so very simple. First thing is there is a current mirroring because gate voltages are same and source voltage is same. There is a current mirroring. Because of current mirroring, 1 milliampere is flowing through 1K 4K resistor. Then it generates a voltage VGS3 is equal to 2 volt. 6 minus 4K into 1 milliampere is 2 volt. Then what is the condition is same current flowing through M4 and M3. Then I equate the current to get V out. Okay, this is a very easy question. Then one more question is in the circuit shown below, all PMOS are identical. The current I is equal to 0. This current is equal to 0. When the resistance R is, so I have to find the resistance R, right? That will make my current I is equal to 0. Okay, yes. So you see, since here I am applying 1 volt, and from here also this node, okay, this node will be suppose Vx. Okay, so current what is I is equal to, okay, 3 volt minus Vx by 3K. Right, current I, this is my current I. Suppose this node voltage is Vx. I am extremely sorry. Okay, this node, so current is nothing but 1 volt, right? 1 volt minus Vx by 3K is my current. So this current I is nothing but 1 volt minus Vx by 3K is equal to 0, already given. Okay, this implies Vx is equal to 1 volt, right? Since Vx is equal to 1 volt, right guys? Now what we have to do? We know this is a non-inverting amplifier. Inverting amplifier. Here the output will be minus R2 by R1 into Vx. So here the output V01 will be, okay, V01 is equal to minus 3K by 3K into input is Vx. So minus 1 minus 3K by 3K is 1, Vx is also 1 volt. So minus 1 volt is my V01. So what is V0 here? V0 will be again minus R2 by R1 minus R2 is 12K by 3K into V01 is my V0. So is equal to minus 3 4 into V01 is minus 1 is equal to 4 volt, right? So V output is equal to 4 volt, Vx is equal to 1 volt. Now let us put in nodal equation at Vx. Okay, So what is that? Current is nothing but Vx minus, this current is I, right? I. Okay. So minus I plus Vx minus 0 by 3k, because this 0 volt, right? Because of virtual ground, plus this current is Vx minus V0 by R is equal to 0. So since I is given 0, Vx is given 1 volt, right, by 3k, plus Vx is 1 volt minus V0 is equal to 4 volt, right? Oh my god, okay, somehow it got erased. Okay, so let me tell you. So this is V01, we got minus 1, V0 is equal to, we got 4 volt, right? 4 volt. So this I am putting a nodal equation here. Okay, nodal equation here is nothing but Vx minus 0 by 3k minus the current is coming into the node is I plus Vx minus V0 by R is equal to 0. Okay, here V0 and I got R2 by R1, I got minus 1. Here again minus R2 by R1, I got 4 volt. Okay, equal to 0. I is given 0, right? This implies Vx is equal to 1 by 3k plus Vx is equal to 1 minus 4 by R is equal to 0. This implies 1 by 3k is equal to 3 by R. Okay, this implies R is equal to 9k. Okay, so I have to put R is equal to 9k for making my current I is equal to 0. So let me tell you briefly. First step is, for I is equal to 0, Vx should be 1 volt. 1 volt. When Vx is equal to 1 volt, V01 is minus 1 volt, V0 is equal to 4 volt. Then we have to apply a nodal equation at the point Vx. If you put a nodal equation, there is an unknown factor R. I can easily find it out. Okay. So thank you guys. That's all for 2019.